Welcome to Programming Fluency. This is Section 6.5 Memory Layout, Stack and Heap. You have been declaring variables, passing pointers, and watching functions receive addresses. But where do those addresses come from? Where does your data actually live in memory? In this video, you will learn how a C program's memory is organized. Let's find out. You have been passing pointers and watching functions receive addresses, but where does your data actually live in memory? Now you will learn how a C program's memory is organized into segments. Let's find out. This is the plan for this video. We start with the big map. When your program runs, its memory is divided into 4 separate segments, and each one has its own job. Next, we look at the text and data segments. This is where your compiled code lives, along with your global and static variables. Then we get to the stack. Every function call gets its own fresh frame for its local variables, and that frame disappears the moment the function returns. After that, we meet the heap. This is memory you request on demand while the program runs. It is a preview of what is coming in Chapter 8. Finally, we talk about lifetimes and their dangers. You will learn about dangling pointers, the trap of returning a local variable's address, and how static storage behaves. Let's start with a puzzle. When you write int x equals 42 inside main, the variable ends up somewhere in memory. When you write int y equals 10 inside a called function, y gets a different address. And now the strange part. When the function returns, y vanishes, but x is still there. Why does one variable survive and the other disappear? The answer is how memory is organized. This is the key idea. A C program's memory is not one big blob. It is split into regions, and each region has a different purpose and a different lifetime. Local variables live on the stack. The stack grows and shrinks as functions are called in return. Global variables live in the data segment, which lasts for the whole program. Your compiled machine code sits in the text segment, which is read only. And there is a fourth region, the heap, where you can request memory at runtime. You will explore the heap fully in Chapter 8. A running C program divides its memory into regions. Read this picture from high addresses at the top, down to low addresses at the bottom. At the very bottom is the text segment. It holds your compiled machine code. This part is read only. Just above it is the data segment. It holds global variables and static variables. These last for the whole program. Next comes the heap. This is memory you ask for while the program runs. The heap grows upward. At the top is the stack. It holds local variables and function parameters. The stack grows downward. Between the heap and the stack is a large gap of free space. The two sides grow toward each other across this gap. One caution. This 4-segment layout is a common convention. It is not a rule of the C standard. The exact addresses and even the segments themselves can differ from one system to another. Let's look at the 2 low segments. The text segment holds your program's compiled machine code, the instructions the CPU executes. This region is read only. If the program tried to write to it, the operating system would kill it with a segmentation fault. The data segment holds global variables, declared outside all functions, and static variables, declared with the static keyword inside functions. These exist for the entire lifetime of the program. Uninitialized globals go in a special subregion called the BSS, which the system sets to 0 when the program starts. The stack is the region that matters most for understanding function calls. Every time you call a function, the system creates a stack frame for that call. A stack frame holds several things. First, the function's local variables. Second, the function's parameters, which are copies of the arguments. Third, the return address, which tells the program where to resume when the function finishes. And fourth, some bookkeeping, like saved registers and the frame pointer. When the function returns, its whole stack frame is popped off the stack. The local variables and parameters are gone. Their memory is reclaimed. Let's see this in action. Here main calls add with X and Y when add starts. The system pushes a stack frame for add on top of main's frame. Inside add's frame live the parameters a and b and the local variable sum. When add returns 30, its frame is popped off, and execution resumes back in main. The output is result equals 30. Now let's picture what the stack looks like at the moment add is running. When your program starts, main gets a stack frame. It holds X, Y, and result, plus a return address. When main calls add, a new stack frame is pushed on top. It holds the parameters a and b, the local variable sum, and a return address back to main. The most recent call always sits on top. Main's frame waits underneath until add is done. When add returns, its whole frame is popped off. The variables a, b, and sum no longer exist. Their memory will be reused by the next call. You can watch the stack directly. Here each function prints the address of one of its local variables using %p_main prints the address of a, then calls outer, which prints the address of b, then calls inner, which prints the address of c. Look at the output. The addresses decrease. Main's has the highest address, outer's b is lower, and inner's c is lower still. Each function call pushes a new frame below the previous one at a lower address. On this system, the stack grows downward. Now the fourth region, the heap. The heap is a pool of memory that you request explicitly at runtime. Unlike the stack, the heap does not clean up after itself automatically. When you take memory from the heap, it stays yours until you give it back. You will learn the full details in Chapter 8, where you meet two functions: malloc, which requests heap memory, and free, which releases it. The heap is how you make data that outlives the function that created it. For now, just know that it exists and grows upward from the data segment. Let's compare the two side by side. Stack memory is called automatic storage. It is created on each function call. It is freed automatically when the function returns. Heap memory is called dynamic storage. It is created when you call malloc and freed only when you call free. The stack variable lives until the function returns. The heap block lives until you free it. A stack variable's size must be known at compile time, but a heap block size can be decided at runtime. The stack is automatic and convenient. The heap gives you control, but you must manage it yourself. Understanding the stack explains one of C's most insidious bugs. Look at bad function. It creates a local variable called local, sets it to 42, and returns the address of local. But the moment bad function returns, its stack frame is gone. The memory where local lived is reclaimed. So the pointer p in main holds an address that no longer belongs to anything. Reading *p might give 42 by luck, might give garbage, or might crash. Most compilers warn you about this. They say, function returns address of local variable. Never ignore that warning. During the call, bad function has a local variable called local. It lives in bad function's frame and holds 42. The pointer p back in main holds the address of local, which is 0x1000. Right now that is a valid pointer, shown by the green arrow. But when bad function returns, its frame is reclaimed. The slot at 0x1000 is now freed and invalid. The pointer p never changed. It still holds 0x1000, but it now points at dead memory. This is a dangling pointer, and using it is undefined behavior. So how do you safely give data back to the caller? You have three options. Option 1, return the value directly. Writing return local copies the value back to the caller before the frame disappears. This is the simplest choice and works for a single value. Option 2, use an output parameter. The caller passes a pointer to its own variable, and your function writes through that pointer. That memory belongs to the caller, so it is still valid. Option 3, allocate on the heap, which persists until you free it. The common thread across all three is simple. Never hand back a pointer to memory that lives in your own stack frame. This is a useful consequence of the layout. A static local variable keeps its value across calls because static moves it out of the stack and into the data segment. Look at counter. The variable count is declared static. It is initialized to 0 once when the program starts, not on every call. Each call increments it and prints it. So calling counter 3 times prints count equals 1, then 2, then 3. Without the static keyword, count would be a normal stack variable, created fresh as 0 every call, and it would print 1 every single time. The scope of count is still local to counter, but its storage and lifetime move to the data segment. Let's finish with a common mistake, the stack overflow. The stack has a fixed maximum size, typically 1 to 8 megabytes. Every function call adds a frame. Look at infinite. It allocates 400 bytes for a buffer, then calls itself again forever. Without a base case, the frames pile up until the stack is completely exhausted. The program crashes with a segmentation fault, also called a stack overflow. The fix is simple. Give every recursive function a base case it will actually reach, so the recursion stops and the frames get popped off. Let's recap. A C program's memory is divided into 4 segments, each with its own purpose and lifetime. The text segment holds read-only machine code, and the data segment holds global and static variables that last the whole program. The stack holds local variables and parameters, 1 frame per function call, popped when the function returns. The heap holds dynamic memory that you request and free yourself, which you will meet in Chapter 8. Because a stack frame disappears on return, returning a pointer to a local variable creates a dangling pointer, and using it is undefined behavior. Static local variables are the exception. They persist across calls because they live in the data segment, not on the stack. Next, you have learned where single variables live. In the next chapter, you will learn about structs, custom types that group several related variables into one compound value.